Welcome back, or welcome for the first time if you haven't been at OCC before. Here comes Nick. Whoop, a minute. So let's see here. So I'm assuming if you are taking this class, you are either a math major or a computer science major. That's pretty much it for folks who come in here. And one of the questions I often get is, what is discrete mathematics? And so the word discrete, in terms of this discrete math, is kind of like the word soup. It's just a big pot full of a whole bunch of stuff. So we'll be jumping around. There's a whole bunch of topics that we're going to be going through in here. But underlying it all pretty much is logic, which is kind of what everything's all about here. So for most of you, this will be the first math class you've ever had in your life. I mean, you may think here comes Oliver. You may think, well, I've been taking math since grade school, right? You go all the way up. In high school, you get geometry, you get calculus, you get all that kind of stuff. And while those are all certainly kinds of math, they're not what real math is. So real math, the word mathematics itself, doesn't even have an agreed upon definition. So it's very strange. So mathematics, one of the most precise kinds of topics that we have, nobody really knows what it is exactly. If you look up on Wikipedia or dictionary or something, you'll see relationships between shapes and area and quantities and how fast and how slow. But mathematics really comes down to just thinking. The word itself comes from ancient Greek, and the word itself just means to see. So the word mathematics is to see and to learn. So what we have, here comes Tyler. So every species has a survival mechanism. Plants and animals, chameleons can change colors. Plants and sunflowers follow the sun. In some sense, the only survival mechanism that humans has is our ability to perceive patterns. And once we perceive those patterns, we can extrapolate from there and make decisions about the future and about the past. A long time ago, before civilization got started, people could recognize weather patterns and growing patterns, and they knew when to plant and when to harvest. You look at the behavior of animals, and we know how to go out and find food and all of that kind of stuff. So mathematics is just all about pattern. And the way we perceive patterns, and we begin to question, so exactly what makes a pattern, what makes a structure, and that's where we start to apply logic. So we have a known set of things that we know to be true. And using logic, we can extend that into something new to be true, and we can keep discovering and uncovering new truths. Knowledge grows, awareness grows. And that's kind of what mathematics is all about. So this will be a very different kind of course. You probably all just finished up a calculus course at some point. And in a lot of sense, calculus is, in my mind, calculus is pretty much just arithmetic. And by that, I mean, you're given a particular rule, the power rule, the quotient rule, the logarithm rule, and you're shown how to solve a couple of problems, and you go home and you try 15 of them for homework, and then you move on. So in that sense, it's just a game of moving back and forth from different sides of the equal sign, left and right, and there's rules to do that. So again, there's a pattern and there's a logical structure to that. So this course is going to get into more about thinking, and oddly more about thinking about thinking. How do we know what we know? How do we know that something is true? Emotions and feelings comes in. Something can feel true. Turns out later it's not. Something can seem implausible, though there's no way that can be true. And we find out later, hey, what do you know? It's true. So this course is going to involve some thinking, learning how to read mathematics, and importantly, learning how to write it. You can have the most wonderful ideas in the world, but if you can't convey it to somebody else, it's not really going to go anywhere. So we want to be able to transfer ideas to each other, and we want to be able to explain something very precisely and clearly, and that, in a sense, is kind of mathematics as well. So this will be very different, and hopefully we'll have some fun. We'll get into some very, very strange things, get into the concept of nothingness, the concept of infinity, touch about religion in here a little bit, because religion and occultism were huge forces in the development of mathematics. You know, why? Why are we here? Where is this place that we are? And we need logic to kind of figure that out. So for those of you who are computer science, which I'm guessing is a significant bunch of you, your computers, all of our computers that are allowing us to like see each other and talk to each other right now, as we all know, based on a whole bunch of circuits that are essentially work by on and off. We have switches, either physical or digital, and they go on and off and on and off, and we have zeros and ones, and it's that logic that makes all of this possible. The rules of that logic that we're going to use were first sort of put into a codified sense by Aristotle 3,000 years ago. And it's the logical rules that Aristotle came up with that run our computers today. So we'll get into a little bit of that. We're going to look at some logic gates. We're going to look at mostly logic. And you're going to be doing a lot of thinking, right? A lot of thinking to go here, and you scratch your heads, and you're going to carry these problems around in your head, and it's going to be frustrating. And all of a sudden, the fog will clear and something will seem crystal clear to you, and you get this feeling of, oh, I got it. And then 5 seconds later, it goes away. So expect to be a little bit frustrated and hopefully have some fun in here. So we're just going to get warmed up today. So now I forgot what I was going to say. It's my first day back after winter break too, so my mind is a little fuzzy. So some of the mechanics. So here we are. The textbook is up in files. Now, everything that I hand out to you, homework assignments, PowerPoints, worksheets, everything this semester is going to go into files, where the only thing there right now is the textbook and the syllabus. So I'm going to upload everything to there after class. And what I'll do is, for homework assignments out of the textbook, I'm just going to do a screenshot of the homework assignments or cut and paste them or something. So you'll get a copy of that up in the book, and I'll say, you know, do numbers, 15, 19, 23, 25, something like that. I'll have worksheets up there. I have maybe some PowerPoints. If I find some interesting little YouTube videos, which I'm always searching for, I'll throw some of those up in there. So every day after class, there's nothing up there now. There will be sort of a warm-up thinking problems after class a little bit. I'll upload that. So make sure that you're able to like download Word documents and that kind of thing. In order to, and I'll repeat this for the next few classes. Every day before class, either late the night before, like Sunday night or Tuesday night, or before class, make sure you check your emails. If for some reason I can't be here, the only way I have to communicate to you is send you a group email and, hey, say I'm not going to be able to be in class tomorrow because I don't know, who knows what stuff comes up, stuff happens. Let me think here. I don't know. While I'm trying to think of what I'm going to say, anybody got a question for me about anything? Because I kind of forgot what I was going to say. Anybody got any questions about anything? Ooh.
How do we submit homework assignments, or do we not submit them?
Yeah, so good question. A little bit about that in the syllabus, not much. I do not collect homework. Even if we were in a classroom, I don't collect homework. The only thing you're really going to submit to me are like graded assignments. Call them whatever you want, test, graded assignment. I don't collect homework, but every day at the start of class, I'm going to say, anybody have any homework questions? And then we'll go over any questions that you have. When it comes to handing in an assignment for which you get a grade, 3 or 4 of you in here were in a class with me last semester too. What you're going to do is write everything out on paper neatly, neatly so I can read it. And then you're going to take a photograph with your phone or camera or whatever. Or if you have the ability to scan it into a PDF document, that's great too. And you're going to email it to me. So when it comes time for a test, I'll send out the test on one day and you'll have like 12 or 24 hours to work on it. So it'll be due like the next day because the problems you're going to get kind of take a little while to think about. Sometimes you can spend an hour or two thinking about a problem and you suddenly realize, oh, it's actually a really easy problem. So you're going to photograph stuff and then send me the photographs. And then I get to open them all up and download them and try and read them on the screen, which is why it's really important to write neatly, which is part of mathematics anyhow. So somebody can write what you want. So I think, Nate, was that you that asked that question?
Yeah, it was.
Yeah, so was that an okay answer?
Yeah, it was perfect. Thank you.
Oh, good. And Anders, are you opposed to us using the math? No, if you want to type stuff, that's great. Learning how to type math, I don't know, how many of you have ever tried to type equations in like Microsoft Equation Editor or something? Typing math, it's a pain, right? But it's a good skill to have because eventually you're going to have to do it. So I know there's Microsoft Equation and there's some other ones. Some of you may have tried LaTeX before. It's a good skill to learn how to type math. Also, the benefit of trying to type out mathematical symbols, like when you're solving a problem, is you kind of have to go slow. And that's where you actually catch little questions, little errors you've made with negative signs or arithmetic. And we all know we do those all the time. So it kind of enables you to think carefully about what you write. So it's a good thing. So Anders, if you want to type up math, that's great. A lot of your answers here, though, aren't going to be like in calculus where it's just all symbols, you know, line by line by line. You get to the end and ta-da, there's the answer. A lot of your answers to these questions are going to be like English paragraphs. You're going to have to explain something in English, how you arrived at a certain conclusion. So you're just going to like send photographs to me, which leads to the fact that it takes me a while to grade things. I don't have a printer at home, so I'm reading everything on the screen and I make little notes to myself and all that kind of stuff. So you're going to have to be patient when it comes time to, you know, when the grades will be posted up there. It takes a while to do it. Plus I have, I think this semester I've got 120 or something students. So, you know, it's my hell when I have to go and grade all of these things on here. That was a good question. Anybody got anything else? Anything else you want to know? Mm-hmm. If we were in a classroom, I would ask how many of you are math majors, but I'm guessing I usually maybe have 3 or 4. See, Mariana, I know you're in here. I know you're a math major. Michaela, I think you said you were going to be a math major. I'm not sure.
Yeah, I'm not sure yet. Either like math or computer science.
Well, they're not a lot different, right?
Yeah.
I mean, in some sense, computer science is just a subtopic of mathematics itself, and it's all logic.
Yeah.
Nate, you're a math major also. Yeah. So here's the thing. So you can declare yourself to, and I'm not like trying to do a hard sell in math or anything, but you can declare yourself to be a math major and still all of your courses can be related to computer science. So instead of, you know, you graduate with a diploma that says computer science, they can say mathematics. And does it make a difference? Well, maybe. So here's the thing. To most people, if you tell them you are a math major, first of all, they'll make a cringy face like they're having stomach problems. Like, oh, and you get stories about how much I hate math and all of this kind of thing. Oh, Carlos, okay, also math. And the other thing is, oh, so you're going to be a teacher, right? Because, you know, people who aren't math majors don't actually understand what math is. A lot of math people don't. But because of that, you can spin it any way you want. If you're a math major, everybody assumes you're smart. So my advice is just keep your mouth shut and just kind of give like a Buddha smile, like, whatever. Say, assume you're really smart. You just go ahead and let them think that. But I remember when I graduated from Penn State, the hot major at that time was chemical engineering. Everybody, bachelor's degree in chemical engineering. These people were walking out of college and getting like $80,000 a year jobs. And this is 30 years ago when 80,000 was more than 80,000 now. And then that all dried up. And suddenly a chemical engineering degree, you couldn't find a job, and they would try to find other things. They tried Wall Street and business, and they would say, oh, we don't need chemical engineering majors. But a math degree, doesn't matter what's happening in the world, everybody thinks you're smart and they figure you can help them out. So the advantage to mathematics is, at the end, you've learned how to solve problems. Doesn't matter what the problem is. Think how often in any kind of course to solve a problem, you have to take it apart, break it into little parts, and you solve each little part, and then you put it back together again. Well, that's kind of what happens in every math course, right? For those of you just out of Calc 2, you're doing like by parts and partial fractions. You break it all down and then you reassemble all the parts. So in one sense, in mathematics, you're learning how to solve problems, and it doesn't matter what the problem is. As we get into logic in this course, I'll probably say a lot, the words don't matter. It doesn't matter if it's a problem in business or chemistry or sociology. You've got this logical structure of a problem. You're here with some givens. So you're given certain parameters and some rules, and you want to put that together in a train of logical thought that ends up in a conclusion, which is the answer. So there's a big advantage to that. And computer science is the same thing. This semester, we're going to be doing things called proofs. You prove, so in mathematics, you want to prove something is true always and forever. But when you're writing a computer program, you're essentially writing a mathematical proof. So in a computer program, you define your variables, and you need to combine those variables and do operations in such a way to have a specific output. Well, that specific output is the answer to the problem, answer to the equation. It's the conclusion of a proof. So mathematics and computer science, very much the same thing. Computer science is a specific form of mathematics on here. So we're going to be learning some vocabulary and some language. We'll begin by doing sort of rules of logic. So what's the difference between, so just for the heck of it, unless somebody's got a question here. Now this logic, there's some words in logic. There's words like and, or, if then, if and only if, and not. And all languages, all human languages have those words. They are something called binary operators. Other example of binary operator in arithmetic, the plus sign, the minus sign, the multiplication sign, and the division sign are binary operators. They tell you how to take two numbers and combine them into another number. So 7 plus 5 combines to be 12. Words like and, or, if then, if and only if, and not combine two words to give us into a statement to give something true. So for example, so today is Monday, or it is April. Is that sentence true or false? Is that sentence true or false?
True.
Yeah, it didn't sound, I didn't hear a whole lot of confidence in your voice, Nate.
I'm not that confident, but
I could hear that. Let me write another sentence. Today is Monday, and it is April. Okay, these are two compound statements. It's a compound statement because this statement is made up of two parts. A simple statement is today is Monday. That's a simple statement. It is April. That's a simple statement. This word or, the binary operator, has combined this into a compound statement. And same here, and is a binary. So, Nate, you're saying that this statement is true.
Yes,
Okay. How about this statement?
I think it's false.
I think it's false. Yeah, well,
It's false. It's false.
nice. There we go. I like that. Well, you're correct. The top statement is true. The bottom statement is false. Now, we haven't gotten into the rules, the algebra of language, which is what we're going to do. But why do you think the first one is true and the second one is false?
Are you asking me specifically?
Yeah, you're the only one talking.
The first one is true because the or makes only one of the statements have to be true. And then for the second one, they would both have to be true for the whole thing to be true.
Nice. So, and all of the rest of you are probably thinking, oh, I knew that. I probably should have said something like that. Oops, wait a minute here. I got to check the chat. Hang on. I got a little behind in my chat. I keep forgetting to look. Oh, no, never mind. There we go. That's correct. So there's actually two kinds of ors. There is an inclusive or and an exclusive or. Language is way more. So by the time this course is done, you're going to be second guessing yourself every time somebody talks to you. And you're also going to become really annoying to your friends and family, because now at the end of this course or during it, you're going to feel more precise about how to use language. And you're going to, like, somebody's going to say something to you and you go, no, that's not what you really said. Here's what you really, but anyhow, we'll get into that. So in this case, the word or is inclusive. And so I see Matthew in the chat and Nate. Or kind of gives us an option. For an or statement to be true, only one of those has to be true, right? It could be both of them true. If I said today is Monday or it is January, the statement would still be true. But just because it is April is a false statement, today is Monday is true. So with the or, only one of them must be true in order to be true. Both could be true. When we have the word and, again, it's called a conjunction. It's a binary operator. For an and statement, all of the parts have to be true. And because this piece is false and the word and, it makes this whole sentence false. Now, we all knew that unconsciously because we have a lifetime of just knowing how language works, even without being able to think about it. And all languages have these, all of them. Well, there may be some very primitive languages that don't, but all modern languages have this. Another use of the word or, so this is inclusive or, only one of these has to be true, or both of them can be true. The exclusive or, which we're not going to use a whole lot of, for you computer science, you may know the word, the three-letter word XOR. That's an exclusive or. So if you remember back in the ancient times when we could go to restaurants and sit down in dim memory of the past, server comes up and says, okay, you're ordering that meal. That comes with soup or salad. So if somebody at a restaurant says soup or salad, what do we know to be true? What do you get to choose if they say soup or salad?
Only one option?
Oh, you can only pick one, right? You can pick both, but you have to pay. So Zane, that was you?
Yeah.
Yeah, we know that means we can only pick one of them, but not both. That's an exclusive or. Exactly one of them is true. The other one has to be false. And we kind of know that without being aware of it. So part of what we're going to do in this course is make ourselves aware of these things. So in computer science, that's very important. We do so many things unconsciously by intuition, and that can lead us to false logical conclusions in here. So part of the thing we're going to do is here, we're going to be paying attention to how we think when we're thinking about solving a problem. So it's not so much just about solving the problem. We have to pay attention to how is our brain working when we do that. So, and that's a difficult thing to achieve. So your brain is going to be focused on the problem, and part of your brain has to step outside your awareness and watch how you're thinking. And that can take a little practice, but there's some rewards in that too. So here's a case where we just did some math. We now have some rules about the word or and this is logic. This is also algebra, by the way. So algebra is much bigger than what you learned in high school. That kind of algebra is just a teeny little piece of algebra. In the biggest sense of the word algebra, which is an Arabic word, algebra, it's essentially all about symmetry and pattern. When you're solving an equation, you have the equal sign, you have a left side and a right side, and algebra is all about the rules about how you can go back and forth from side to side. Well, that applies to things way beyond numbers and equations. Symmetry is very important. And I don't know if some of you had chemistry. There's things called stereochemistry and optical chemistry. It's all about how symmetry works. So we'll get into some of that stuff there. So like I said, in many respects, this is the first real math course you've ever had. I'm assuming a bunch of you have had geometry in high school. I'm assuming almost probably all of you have. And generally in high school, everybody hates geometry. Kind of boring, and when am I ever going to use this in real life and all that. Geometry, if you've had geometry, is the closest thing to real math you've had, because geometry is essentially logic, right? You learn all these rules about interior and exterior angles and complementary and supplementary. And you do all these proofs forever. It's proof, 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 proof. And it's pretty boring when you're in high school because other things are going on in your life. So that's probably the closest you've had to real math if you had it. I've run out of things here. Has anybody got any questions yet? I've been teaching for a long time and I never know what to do on the first day. I just let my mind kind of ramble. As far as mechanical stuff, so you got the book. Office hours, quote unquote office hours. Here's how we do office hours. If you want to get together like outside of class and talk about questions and things like that, all you have to do is send me an email, and I'll be reminding you of this for a while. Send me an email with three times that you are available. Like give me a day and a time, and it can be Sundays, it can be Saturdays, it can be 10 o'clock at night. Just like most of you, I got nothing else going on in my life except this. So if you have jobs and classes or families to take care of and all of that, and you got like this burning question that you want to get together or talk about something during a quote unquote office hour, and the only good time you can maybe make it is like 9 o'clock on a Thursday, let me know. I'm probably going to say yes. So if you give me three options of times, I can figure out which one fits best into mine. I may have a class at one of those times and can't meet with you, or I might have something else going on, which I don't really have anything else going on. So office hours, we'll just arrange a one-on-one Zoom, and it will be the same ID and password as you use to get into this class. That's going to be the same all semester long. Let's see, what else do we need to say? Well, let me throw something out while I'm thinking of it. So here's a statement. Okay, so here's a binary operator called an if-then. Here's the word if, here's the word then, and they never, ever can be separated. You cannot have a statement with the word if, a sentence or a statement with the word if without having the word then. even though you may not explicitly say the word then, it's always going to be in there. An if and a then are always in pairs, even though one of them may not actually show up in the words, it's still hiding in there. In any language, by the way. So that statement, true or false? False. Okay, Michaela, why is it false? Yeah. So how many numbers are there? How many numbers exist? Oh, infinite. Yeah, so what does that actually mean? Oh, we'll get to that. Nobody really knows what infinity is, by the way. We think we do. So there is an infinite quantity of numbers. There's all kinds of numbers, by the way, all kinds of different kinds of numbers. So if a number is not positive, then it must be negative. This statement is false because there is exactly one exception. The number 0, so this is false. And it is because of this, my favorite number, the number 0. So if we think of the real number line, and that funny little R, oh, and I'll get rid of this glare for the next class. It's coming in the windows back there. So if we think of the real number line, x-axis for lack of a better word, we put 0 here. All the numbers to the right of 0 are positive. All to the numbers to the left of 0 are negative. So 0 is what defines positive or negative. So out of all the infinity numbers, this is the only one that is neither positive or negative. So 0 is a very interesting number, by the way. I really like it. If I'm adding, subtracting, or multiplying, I never make a mistake if there's a 0 in there. But then we come to division. We try to divide by 0 and all kinds of crazy things happen, right? So what happens when we divide by 0? Well, Anders, I'm going to disagree with you. 0 does not represent nothing. 0 is a counting number. 0 is not a nothing. 0 is a counting number. It defines a quantity, and a quantity exists. 0 means you don't have any of that thing. It doesn't mean you have nothing. It just doesn't, it means you don't have that thing. If I'm counting elephants, I can say there are 0 elephants in my hand, but yet in my hand is not nothing. In my hand, there's molecules and air and dust and all kinds of stuff in there. So we will eventually this semester get into the concept of nothingness. And nothingness and infinity are very closely related. So 0 is actually a counting number. Now, 0 has an interesting history. You've probably all seen, maybe in high school, you dealt with Roman numerals and stuff. Roman numerals, they look nice on a clock, but they're not very practical. You want to multiply two numbers together with Roman numerals, you kind of have to convert them first, because Roman numerals don't have a place value system, because there was no 0 to occupy a place, not where there's nothing, but where there wasn't a digit in that place. So the concept of 0 as a number came out of sort of India, Persia, that kind of area, Southeast Asia. And it worked it up as trade grew in global civilizations. It worked its way into the Middle East, where the development of algebra, again, Middle Eastern word, Arabic word, and eventually made its way into Europe in the 1500s. And for a while in Europe, the church, and back then there was only the church, there was only one of them, it was forbidden to use the number 0 because you could prove God doesn't exist. You could use the number 0 to prove God doesn't exist. The logic was wrong, by the way. They didn't actually prove anything, but the church was afraid of the number 0 because it brought into the concept of religion. So we'll get into some of that. So that statement is false. Yeah, all kinds of numbers. We're all familiar, I hope you're familiar with integers. What kind of number is an integer? Anybody happen to know? There's other words we use for integers. Yeah, integer is a whole number. 1, 2, 3, 4, 5, 6, 7, 8, 9, -10, -5, -4. So integers are whole numbers. So if an integer, if an integer is not odd, then it must be even. True or false? True or false? Michaela thinks that's true. Okay.
True.
True, but not a whole lot of confidence in that voice. That was you, Sean?
Yeah.
True. You're thinking true, but you're maybe thinking you could be wrong. It turns out that yes, this is true. For those of you who weren't sure, I'm guessing you were thinking of one number, weren't you? What made you hesitate, Sean?
I just trying to remember if I know it sounds probably a little dumb, but I just think I'm not gonna lie, I thought 0 was part of an integer. That's why.
Yeah. So here's this number again. Well, first of all, 0 is an integer. It's a whole number. And back to what Anders said, it's a counting number. I have 4 bananas. I have 3 bananas. I have 2 bananas. I have 1 banana. I have 0 bananas. So you're actually counting something. You're saying how many you have of something. So 0 is an integer and 0 is even. 0 is an even number, an even integer. If we think of how the integers go, so if we have -4, -3, -2, -1, 0, 1, 2, 3, and on there. So every other integer is even odd, even odd, even odd, even odd. So 0 is an integer. It's also even. What defines what makes an integer even? What's the definition of an even integer? How do we define an even integer? Divisible by 2 is the most common way to say that, and that's correct. But it's not mathematics. It's not the way we say it in mathematics, because there really is no such thing as division in mathematics, and I'll get into that later. So 0 is even. So definition is a definition of even integer. So the definition of an even integer. An integer, and I'm going to use a lowercase n. So a lowercase n is going to be our symbol all semester for an integer. An integer n is even if and only if, and there's a logic thing, if it is 2 times another integer. Which is equivalent to saying divisible by 2, like Michaela said in the chat room. But in mathematics, we define an even integer by multiplication. So n is even if n is equal to 2k, where k is an integer. So that's how we define an integer in mathematics. And we'll get into this later. This little arrow is the mathematical symbol for the words if then. The back end of the arrow is the if part. The front end of the arrow is the then part. So this says if n is even, then n is equal to 2 times k, or k is another integer. So that's the mathematical definition of an even integer. So 8 is equal to 2 times 4. 20 is equal to 2 times 10. 0 is equal to 2 times 0, and 0 is an integer, so by definition, 0 is even. So this is just some of the like precision that we're going to bring to things. So saying a whole number is even, if you can evenly divide it by 2, is a perfectly reasonable explanation. But using this form of an integer, writing even integers as 2k, will allow us to do some other proofs about numbers. So where we get into form and structure and we try to avoid words. So an odd integer, so the definition of an odd integer then, how would we define an odd integer? Well, we could just say it's not even, which would be correct. So integers have to be even or odd. So here's an exclusive use of the word or. An integer must be even or odd, but cannot be both. It has to be one or the other. So how would we define an odd integer? So if m is odd, and here I'm using a lowercase m to distinguish it from lowercase n. I'm just saying it's a different integer. Well, if m is odd, then m has to equal what? How would we define an odd integer using this sort of thing here? Yep, Nate, that's good. So we could say, so 2 times k, that makes it even. And then if we add or subtract a 1, so we could say 2k plus 1, we could say 2k minus 1. Both of those are algebraic expressions of an odd integer. Sometimes the plus 1 is better, sometimes the minus 1 is better. So, whoops. So this just gives you a sense of, we want to remove words in a sense. We want to remove opinion and give ourselves precise definitions. Oh, I'm sorry, that glare is really awful. I'll have that fixed for you next time. Okay. Well, that's worse. Well, anyhow, once we have a precise definition, we can use rules of logic to come up with something new. So for example, we know that 2 plus 4 is 6, 20 plus 100 is 120. We begin to suspect that if we take 2 even integers and add them, the result will be another even integer, right? And we can keep coming up with examples all the time, and we begin to suspect that's true, but suspecting something true is not good. We want to be able to conclusively prove that it is always true. So we'll get into some methods of how to prove something that is using an airtight logic, which is kind of what math is all about. Yeah, so that's just a little bit of a flavor. It gets a little more involved on this. So let me see, what else was I going to say? I keep forgetting about what I want to think about here. Anybody got any questions or anything? Doesn't have to be about this, but questions that have popped into your mind while we've been going over some stuff?
Do you have any idea what the schedule of the class will be? So like how often we will have graded assignments throughout the semester?
There will be at least 4. There will be at least 4 graded assignments, and they will happen when it's an appropriate time to have them happen. I don't have specific dates. You know, we'll get to a point where we'll finish maybe a topic and the next topic is very different, so we'll have one then. Or we'll get to a point where maybe I think that's enough for one assignment. But there will be 4, possibly 5 graded assignments here. And Jared, the grade breakdown. You'll have 4 or 5 grades at the end of the semester. I add them up and divide by however many. That's it, just a straight average. So if we have 4 tests, I'll add them up, divide by 4. If we have 5, I'll add them up, divide by 5. Pretty much how that works. No fancy stuff going on there. So I hope that answer was, well, probably wasn't satisfying. I don't have specific days. You'll know ahead of time. And as I said before, the tests are not timed. The test doesn't happen during a class, and at the end of the class, you have to be done and send it to me. I'll send you a test on one day, and it will be due at some point the next day. So you have like a whole day to work on them.
Sounds good. Thank you.
Matthew, I do, but I haven't done it in a couple of years, and I'm not doing it this semester. That's as good as I can tell you. I don't know what next semester will be. I won't find out what I'm teaching. We don't get to pick, unfortunately. I don't know what I'll be teaching next semester until along about probably April. Our schedules will come out about what we're going to be doing. And as far as next semester, for those of you who are still going to be at OCC, I have no information one way or the other of what that semester is going to look like. The general feeling is plan on it being remote, and then you won't be disappointed if it happens that way. So, you know, the world is crazy as it is. How likely it is by September that we're all going to be sitting in a classroom together, my guess is probably not all that likely. And if we are, it's going to be very, very different. You won't be sitting in a classroom with, 25 people probably. So we just had a meeting a couple days ago to kick off the semester. And right now the plan is nobody knows yet. Nobody knows what's going to be happening. So anyhow, as far as Calc 3 next semester, I have no idea. I'm not even sure that I'll be teaching next semester. I'm thinking I may just like take a break for a while, throw a sleeping bag in the car and go on a road trip for a couple of years, but I haven't really decided yet. So let's see. So I don't know, first day we kind of got warmed up, give you a sense of things. The takeaway here is it's going to be different sort of class, right? Yeah, there's going to be numbers and symbols and all that kind of thing, but it's all going to come down to thinking. And there we are. So I don't really have anything else to say too much. I'm going to upload. I have another class right after this one. Starts at 12:30. I have a statistics class. And those are the only 2 classes I have on Monday. So this afternoon, I'm going to upload to files. Everything I do goes into files. So if you miss a class or something, just go there. You'll see the assignment for that day. If you want to meet me out of class, send me an email. We'll figure out a time that works for both of us, and we'll have a one-on-one Zoom. So I'm going to put some questions for you to think about up there today. Just sort of general, figure it out kind of questions. And then on Wednesday, we'll start up with some more structured kind of thing. We're going to start with logic. I believe in the textbook, it's chapter 2. So you can start to like look over it. This textbook, by the way, I've been using it for years, and I've been teaching for a long, long time, is one of the best intro to logic textbooks for mathematical computer science people. So the prerequisite for this course is either Calc 2 before or Calc 2 the same. There's no calculus in this course. That's kind of, calculus is considered continuous math. This is discrete math. So in the sense, discrete is pieces, right? Integers, 1, 2, 3, 4. There's nothing in between. Logic, it's going to be yes, no, true, false. So calculus is all continuous stuff. But the reason calculus is a prerequisite is because you're used to looking at symbols and formulas and just reading it like a language. That's the reason for it. So there'll be a bunch of that, learning how to read all that kind of stuff. But ultimately it comes down to just sort of thinking. So I'm going to put some just random thinking problems up there this afternoon. Take a look at those. We'll kind of go over them a little bit on Wednesday. So anybody have any final questions or anything? Well, I don't know about all, so this was my very first class of the very first day of the semester, so I guess my brain is starting to get back into the swing of things a little bit. Well, all right then. Oh, crap. I forgot to record the class. Usually I will be I will, other than today, because I forgot to hit the button. I did, oh, Rebecca, I did. What does I did mean? You have a question? Oh, you recorded it. Oh, bless you, bless you, bless you. Can you, let me see, you can't upload. I don't know if you'll be able to email that to me because the file is too big. Does it show how big that file is? Is it possible you might be able to email it to me? Thank you so much. I forgot to hit the button, which reminds, I will be recording all of the all of the classes. Although at the beginning of every class, remind me if you don't see, if I hit this button, you should see now that it says recording up there. If you don't see that when I start my classes, please remind me. And I will be uploading the recordings into files where everything else goes. So if you miss a class or you want to see something again, it will be up there for you. However, there's a limit on how much data I can store in Canvas for the class. I can keep maybe 3 lectures up there at a time, and then I have to start removing the old one to put the new one in there. So if you can download them and want to keep them, that's fine. So I wanted to say that. One of the things I forgot. Well, all right then. So this will do it for the first day. And I guess I'll see you all back here on Wednesday. Right? And again, remember to check your emails before class. If for some reason, I don't know, the weather's going to be bad, I live in an old building, the internet goes out or something, I can still email you from my phone and say, you know, class canceled today or something like that. All right then. So quote unquote, nice to sort of see you. And we'll be back together again on Wednesday, okay?
Awesome. Thank you, Professor.
All right.
Thank you. Have a good day.